Hello, everyone, and welcome. My name is Jaskolka. I'm an associate professor at the Department of Systems and Computer Engineering at Carleton University. And we're going to be hosting this next session of SECREV 2024. So our session is titled Securing AI-Based Systems from Design to Operations to Assurance. So to kick our session off, I'd like to give a few opening remarks and start by telling you a little bit about ourselves, what you can expect in this session, and I will tee up all of our speakers for today. So to start us off, I'd like to give you a little bit of information about the Cybersecurity Research Lab. That is the lab that I am the director of at Carleton University. And our mission within the Cybersecurity Research Lab is to conduct academic research to develop systematic and rigorous approaches for evaluating and ensuring the cybersecurity of software-dependent systems. So within this lab, we have a number of master's and PhD students. We also have a number of undergraduate students that join us from time to time, and we collaborate with several academics throughout the world. Within the lab, we have a number of different areas of research. So this slide here summarizes a little bit of what we do. So our main focus is providing cybersecurity evaluation and assurance. And this comes in a number of different forms. Our basic research thrusts include developing security analysis methods for a variety of systems. We focus on ways to improve decision-making for cybersecurity. This involves the development and analysis of different security metrics and measures. We focus on developing security design patterns and architectures. We look at different methods for threat modeling and understanding the threat landscapes that we have for a variety of systems. We develop security assurance cases and analyze security assurance cases. We look at issues of security compliance with respect to standards and regulations. And we develop tools to support engineers and developers in building secure and trustworthy systems. And the foundations for these different research thrusts lie in the areas of software architecture, software requirements, model-based engineering. We focus on data-driven approaches, formal methods, logical specifications, and finite state machines. And we apply a lot of our research in a number of different application areas, namely critical infrastructures and industrial control systems. We also look at the Internet of Things, cyber physical systems, distributed systems, as well as AI or ML-based systems, which is really where the focus of our session is going to be today. So to give a quick overview of our session, I'd like to start by giving an overview of what we really mean when we say that we're securing AI-based systems. So in our context, we're going to consider an AI-based system to be any computer system that employs artificial intelligence based components that perform certain tasks that typically require human intelligence. And these components are often integrated with a number of other components within the system, and they all interoperate together to achieve some sort of functionality. Now, these AI-based systems have a number of interesting capabilities. They can learn from data, they can recognize patterns, they can make decisions, and they can continuously improve their performance. Now, these AI-based systems can encompass a wide range of technologies, and this includes machine learning, deep learning, natural language processing, computer vision, and much, much more. These types of systems are used in various fields, such as healthcare, in finance, in manufacturing, customer service, transportation, among a wide variety of others, to automate different tasks, gain insights from data, and enhance decision-making processes. Now, as a result of these types of systems being used in these critical domains, security has become a top priority and a necessity for being involved at all stages of the system development and operation. Now, this, of course, comes with a wide variety of challenges for developing and operating these types of systems. We have the challenges of dealing with the traditional parts of the systems, the components that do not use AI or machine learning, for example. as well as the new challenges that come from the emergence of these technologies within various components of the system. So on the slide here, we have a basic overview of a system development process. And the presentations and discussion during the session today are going to explore a number of the challenges and opportunities for engineering secure systems that employ these AI or ML-based components, these AI-based systems, as it were. We're not going to have time to cover every single stage of the system development lifecycle. But what we have here is in the light blue, all of the different stages. We're going to focus on the dark blue stages, namely the architectural design and the operation and maintenance phases. The red boxes in the diagram refer to the security activities that are performed throughout the different life cycle stages. And we're also going to focus a little bit today on the security assurance activity from the security side of things. So this gives a basic roadmap of the types of things that you're going to hear about throughout our session today. So what I'd like to do now is introduce the various speakers that we're going to have for our session. So as I mentioned, the Cybersecurity Research Lab at Carleton University has collaborations with a number of researchers around the world. I'm very pleased to welcome today Marwa Zeroual, who's a PhD candidate at the University of Paris SECREV and part of CEA within France. And she's going to be providing a discussion about ML security challenges at the architectural level today. Following Marwa is a PhD candidate at Carleton University within the Cybersecurity Research Lab, Xinrui Zhang, and she's going to be talking to us about conceptualizing the secure machine learning operations, or SecML ops paradigm. And I'll close our session today by providing a short discussion about different security assurance challenges and approaches for dealing with the security of deep neural networks. So we have a wide variety of presentations, and hopefully we can engage in some really interesting discussions throughout our session today. So without further ado, I'm going to turn over our session to Marwa, who will give us our first presentation. So Marwa, please take it away.
Thank you, Jason. So I will recall that I'm a PhD student from the University of Paris-Saclay in France. I'm working on security assurance cases for systems based on machine learning. And today I'm glad to share with you a part of the work I'm doing. I will be focused, as Jason already said, on the design phase, particularly on the architectural level. And we will seek to see what are the ML-specific security challenges that appear at that phase of the development life cycle of a system. So I'd like first to start with an introduction and motivation that justify the interest we are giving to the topic of ML-specific security challenges. Then we'll see the software architectures and the modification that an ML component bring to the software architecture. What are the KML specific security challenges that result from incorporating ML components? And finally, we'll conclude with remarks and some future ideas for future works. During the presentation, I'll be using and reusing some concepts. First of all, security architecture. By security architecture, we design an architectural design that includes all threats, potential risks, and the security controls and solutions we propose to mitigate the identified threats. By machine learning based systems, we mean systems that incorporate components developed using ML techniques. And finally, we'll be focusing on ML specific security attacks, which refer to the attacks that results from exploiting the vulnerabilities in the machine learning development lifecycle. So we will be ignoring the conventional attacks that are already seen in systems that don't necessarily use machine learning. Our work is part of the paradigm of secure by design principles. Our idea is to deal with security in the design phases, particularly for machine learning based systems, as they depend heavily on the software architecture, on the security of software architecture in our context. And with this idea of addressing the security issues at the architectural design phase, we will be having the following advantages. First, it allows us to early detect and mitigate the security threats, which in turn will allow us to reduce the time and the cost of fixing the vulnerabilities later after the deployment of the system. And also it provides like a strong foundation for the implementation of security measures in the following software development lifecycle phases. As I said, bringing machine learning components into a system raise new challenges due to some characteristics of these ML components. First of all, they are known to be non-predictable, which means that even if we know in an input, we cannot predict or know in advance what would the output be. They are also non-interpretable, which tackles the explainability of the machine learning models. It means that we cannot understand or justify or interpret the decisions made by an ML component. A third characteristic that raises in turn some security challenges is that they are non-deterministic, they are uncertain, and they always output a range of possible prediction and a confidence score. So, as I said, these ML characteristics raise new security challenges, especially because the already established knowledge related to the security engineering processes was conceived initially to conventional model-based systems, so they don't take in consideration machine learning systems. And even in the industry, we don't have the new knowledge or new security standards that will allow us to deal with these ML-specific security challenges. And also, the conventional way of doing things using testing, model verification, and validation is not enough, unfortunately, to deal with the ML specific attacks. So, in the context of this talk, we will try to set the different ML specific attacks in the architectural level. To do this, we start by recalling like generic ML based generic architecture for ML based system with respect to the different phases of the development life cycle of an ML component. So it goes through 4 stages. It starts by like a deep understanding of the problem, of the problem or of the task that requires intelligence. We try to specify the requirements that we have to respond to. After we collect data from different sources, as we know, machine learning are data driven paradigms, so it's all about data. We try to collect data and prepare them to have the training data that responds the best to the requirements we have already defined. After we move to the stage of model management by selecting the suitable machine learning model that will allow us to respond to the requirements using the collected training data. We effectively start the model training using the training data. We test and verify the model one more time before its deployment. when the ML model finally is deployed in a system, we are in the operational stage. We have a machine. We have a model that sends inputs to the machine learning model, and another one that recovers the result and use them to do, I mean, according to the result returned by the ML model, do the task for which the machine learning component was designed initially. To make things more concrete regarding the steps of the development life cycle regarding the components in a generic architecture, I would like to focus on one task that's like successfully assured by machine learning techniques, which is the classification task. So the basic idea of the classification tasks is to have a list of inputs and to classify them to the suitable class label. So we will see what each component of the generic machine learning based system architecture will be used to realize the classification task. So we will be collecting first raw data. It might be videos, photos, texts, and so on. We prepare them by defining a set of features that will help us to characterize the data and to build a training data where each entry in the training data is a couple of input and output. I mean, the input is the data to classify, the output is the class label. After that, we start the learning process in order to extract a function that maps in the suitable way the inputs given in training data to the right outputs as it was defined in the training data. Once the training is done, the verification and tests of the ML model is done, it will be deployed. The ML input is supposed to send inputs that have not been seen in the training phase and will ask the ML model to assign them to the right class, and the class will be, the class label will be returned to the ML output component. Going back to the generic ML-based system architecture, we can identify like three big families of ML-specific security attacks. We have the poisoning attacks that appears in the data management stage. Its goal is to modify the training data in order to make in order to influence negatively the training process and to produce ML models that doesn't do the task in a good way. The second family of ML specific attacks is the inference attacks, which aim to create a surrogate model that is functionality is equivalent to the target model. So we are trying to infer some sensitive information from either from the training data or parameters from the ML model. And last, we have evasion attacks, the famous family attack that happens in the operational stage with the goal to change the classification label for inputs via making some small variation. What comes next, we will be seeing each attack deeply, how it happens at the architectural level or of a machine learning based system that is used to do classification task. So let's start with the data poisoning. As I said, it compromises the training data set. We have here initially, like in the suitable case, we have a training data with inputs and the right or the suitable outputs. we are presenting here the ML model function as a function that goes from the set of the input X to the set of the outputs Y. We see in the representation that it classifies in a good way, and it succeeds to distinguish the purple class from the green class, which which is the initial goal for what the ML component was trained. After once the data poisoning attacks is happening, the idea is to go to the training data and to modify the outputs of some inputs, which will falsify all the training process and will produce a non-accurate ML model. So if we see here, we notice that the function F2 that result from the poisoned training data is not classifying in a good way the new inputs. I mean, we are seeing that it misclassify part of the purple class and part of the green class. Another ML specific attack is the model inversion. So the goal is to try to infer an input from the training data having some auxiliary information. So in a sane configuration, we have an ML input that sends some input to the ML model, which return the right class label. The attack model of model inversion here is the configuration when we know some features, we are looking for some missing features that will enable us to have a full input that will return the label, a specific desired label. So in a more concrete example here, the attackers have succeeded to reconstruct an image by using the model inversion attack against a facial recognition machine learning based model. So the idea is that they only know the name of the person and the confidence score returned by the ML component. They start putting arbitrary values for the missing features until they succeed to build this image that allow to have the best confidence score. And initially this image was supposed to be protected in its part of the training data, and it was supposed to be confidential. So using the model inversion, they succeed to violate the confidentiality of the training data. Another ML specific attack is the model extraction one. It's an exploratory attack with the goal of inferring the functionality of the model. So an attacker starts querying the ML model and collecting new training data. So it sends different queries and recover the outputs returned by the ML model, which allows the attacker to build a new training data that will be used to train a new surrogate ML model that will try to imitate the functionality of the targeted ML model, which also violates the confidentiality of the ML model. Another exploratory attack, which is similar to the one in model extraction, it's membership inference. So the idea is to start querying the ML model and to collect new training data. The difference is that for model inversion, our goal is to to produce like a second ML model that has the same functionality as the targeted one. For the membership inference, the goal is to build an ML model that succeeds to distinguish if an input was part of the training data or not. So we will be recovering the results of querying the ML model. We build the new training data, and in the same way, we will train a new ML model using the results of querying the targeted model. So it's also an attack that violates the confidentiality, but this time it's confidentiality of the training data. Now we move to one of the attacks that happen at the operational stage. It's adversarial example, the like the most dangerous and the well-known attack. The like in a suitable configuration, we have always an ML input that sends some input to the ML model, to the classifier in this time, in order to get a class label. The idea of adversarial example is looking for a small perturbation to add to an input to form a new input that will succeed to deceive the ML model in order to get a different class label. In a more concrete example, we have here an ML model that is used to recognize traffic signs. We are seeing here that it succeeds to recognize that the photo of stop sign is a stop sign. However, by adding a small perturbation, and technically a perturbation is a modification of some values of the features that compose the initial input, we build a new adversarial example that for us looks like the original one. I mean, we all agree that it is a stop sign. However, the ML model returns, recognize the new stop sign as a max speed sign due to this small perturbation. Which like we can imagine how catastrophic the results of these kind of manipulations could be. To conclude, I would say that securing machine learning based system is challenging, and we propose to start seeing or dealing with the ML specific attacks at the architectural phase to gain what we have already mentioned, to reduce the cost and to gain time in fixing them. And according to the machine learning techniques particularities, new security attacks might appear. For example, if we consider like a configuration where we have an online training, which means that the machine learning keeps learning even in the deployment phase. Here we will be seeing new ML specific attacks appearing, such as the ML model reprogramming attacks. And finally, addressing these challenges requires a combination of a robust defense and deep understanding of both ML algorithms and traditional security principles. So this was my talk. Thank you. And if you have some questions, you can put them in the chat.
Thank you very much, Marwa, for your presentation in our session. We're going to, if there are no questions coming in, which I don't see right now, we'll move right along to our next presentation. So our next speaker is Xinrui.
Thank you, Professor Jason, and thank you, Marwa, for the great presentation. So now I will share my screen. Okay, hello everyone. My name is Xinrui Zhang, and I'm a PhD candidate in Carleton University, and I work under the supervision of Professor Jason Jaskolka in the Cybersecurity Research Lab. Today I will be presenting conceptualizing the secure machine learning operations paradigm. This work has been published in IEEE International Conference on Software Quality, Reliability, and Security in 2022. Okay, here is the outline of this presentation. First, I will give an introduction, followed by a background of MLOps, DevOps, and SecDevOps. Then I will introduce the proposed methodology, SecMLOps, in terms of its conceptualization, challenges and solutions, and the impacts on other qualities. And then I will conclude by seeing some future works. So nowadays, machine learning has gained increasing popularity in the industry, especially in some critical domains such as healthcare, transportation, infrastructures, and so on. Within those machine learning-based systems, security is a paramount concern that we cannot ignore. However, managing security is not easy because it faces intrinsic and extrinsic challenges. Those systems are usually very large-scaled. Therefore, it has a huge complexity in machine learning development lifecycle. And they could include hardware, software, clouds, plus machine learning model itself, and that also enlarge the attack surfaces. The machine learning model also suffers from the lack of explainability, especially in deep neural network. Externally, there are various attacks targeting our machine learning-based systems during the whole life cycle, as Marwa just introduced. Therefore, we need a way to consider security in machine learning-based systems explicitly. So due to the need of machine learning applications, machine learning operations or MLOps was coined or effectively develop, deploy, and manage machine learning models in production. Its basic idea is to apply DevOps into machine learning. DevOps is the most popular software engineering paradigm. And when it is introduced in machine learning, it introduces the automation and, for example, the automation and monitoring at all stages of building machine learning. However, MLOps does not provide a clearly consideration for security concerns. And for DevOps, the SecDevOps or DevSecOps was proposed to integrate security right into DevOps. With similar spirit, we first proposed SecMLOps. And here we define our SecMLOps as it promotes the explicit consideration and integration of security within the whole ML lifecycle to result in more secure, reliable, and trustworthy ML-based systems. And we conceptualize it in the aspect of people, process, technology, and governance and compliance. Or we call it PPTGC framework. Since MLOps is unavoidably based on, since SecMLOps is unavoidably based on MLOps, we have chosen to adopt the work by Grisberger, which is to say the most explicit work we found on MLOps. Now I'm going to introduce the people aspect in SecMLOps. So in terms of the people, we have 6 roles from SecMLOps, and we describe the roles and the responsibilities for SecMLOps in terms of each roles. For example, for role 1 and 2, external security expert may be required to finalize the security policies and perform security analysis to help the system followed by security by design. And for the rest of the role, there should be at least one person specialized in security with specific security knowledge and capability. For example, the role 7, MLOps engineer, they should have comprehensive knowledge of security in both machine learning and IT because they need to communicate and manage the cooperation between the rest of the roles. And for the aspect of process, we have present the security aspect in 3 stages: the design, experiment, production, and overall. In the design stage, the overall security objectives such as confidentiality, integrity, and availability, and their requirement of machine learning systems should be clearly defined. And this should particularly include the data and the ML model. And then in the requirement analysis, machine learning security models such as machine learning attack surfaces, threat models, attack or adversarial models should be performed in order to understand the potential threats and countermeasures. And this understanding plays a very important role in achieving the security by design. At the architectural stage, when it is less costly to make changes and build security policies from a holistic view. And next, in the experiment and production stage, the security policies should be obeyed and constantly updated during the MLOps lifecycle. The security policies should include machine learning related areas such as data security and model security, as well as the IT-related areas such as physical security, personnel security, administrative security, and network security. Before the model is exported, security evaluation should be performed to assess the robustness of the machine learning systems in a simulated adversarial setting. And in the monitoring component, security monitoring and incident response should be implemented and guided by the security policies. And in the overall aspect, it is important to keep useful knowledge in a shareable way. This can include, but not limited to, adversarial attacks and defenses, approaches to establish security policies and their effectiveness, and the rationales of chosen and proven techniques, tools, platforms involved in the machine learning workflow. Okay, in terms of the technology, there are many tools and platforms for MLOps. We have summarized the security control of some existing tools in the table and presented part of it. Please refer to our paper for the complete table. Let's take supervisory as an example. It is a commercial data processing platform that has role-based access control, encryption of data at rest and in transition, single sign-on authentication, virus scanning, and network isolation as security features to protect from adversaries. This platform is also compliant with GDPR and HIPAA regulations. It is essential to keep the security features, to consider security features when selecting tools and platforms according to the system security requirement and budget. For governance and compliance, organizations should present the system's compliance to specific security requirements required by the law, follow the related standards and guidelines, establish security policies, use metrics to evaluate performance and how well SecMLOps is implemented. Okay, now I'm going to talk about the challenges in adopting SecMLOps and its suggested solution. In terms of people, there's a typical lack of attention and care about security, which may be caused by the lack of knowledge and understanding. Also, there's a constant shortage on security experts and personnel, and security experts with a machine learning background are even more rare. Therefore, therefore it is challenging to fulfill all roles that SecMLOps requires. And the main idea of suggested solution is to form a people-centric security that can be achieved by offering security training programs for different roles, organizing security-related activities, assemble AI red teams who take adversarial approaches to expose vulnerabilities with the goal of making systems more secure. In terms of the technology, we have conducted a small empirical studies by randomly choosing 20 tools or platforms and examine how obtainable documentation is about their security features. The result shows that most of MLOps tools do not have security features, and more than half of them do not provide a clear introduction of security features that can be easily navigated. So according to the situation, we recommend people to extend tools and platforms with security features. And if for those they already have that, just to make them more explicitly presented and also present them as one of the key features that can be easily found. So in terms of the governance and compliance, the challenges includes it's very difficult to find suitable standards, and those standards are usually lack of details on how to prove its compliance. And there's also a lack of automated tools to check machine learning systems compliance. The suggested solutions, we advocate more works in this topic, and we hope people to build more tools on automated machine learning compliance checking. In terms of the process, the challenges, of course, includes all other mentioned challenges because it requires people, technologies, and the compliance and the governance to finish the process. It is also difficult to manage and operate complex systems, which is the nature of many machine learning-based systems. And there's a big trade-off between the performance and expenses when considering security. So our suggestion is to solve other challenges first, and also stick to a process with security consideration, and also perform the trade-off analysis. So now I would like to briefly talk about the impact of SecMLOps on other qualities. First is the fairness. Strengthening the security of ML-based systems could have a positive impact on fairness due to the similar requirement of pre-processing data. When the system have data of all kinds and with equal distribution, then the model will train to see all various of inputs and be more robust from the model who only sees one type of the input. In terms of explainability, following SECREV could help release the burden of root cause analysis when unintended explainability issues arise in ML-based systems. This is because we can quickly exclude certain aspects of possible fault by following the security policies and having relevant security process documented. In terms of the reliability, making machine learning-based systems secure is the foundation to make them more reliable. The reliability means the machine learning-based systems constantly perform well over many decision-making tasks, and it requires the system to be secure in each one of them. In terms of the security and safety of machine learning-based systems cannot isolate one from another. And the essential idea of making systems safe largely overlap and align the goal of SECREV, such as considering safety early in the design phase, building ML-based systems that can endure unusual, extreme, and adversarial events. For sustainability, although some efforts requires in adopting SecML, it is beneficial in the long term due to less re-engineering is needed for security purpose. Because less re-engineering due to security issues is needed, and the security mechanisms can be adopted and reused in similar cases. So in conclusion, we have defined SecML and conceptualized it under PPTGC framework. We also discuss the challenges of adopting SecML and also propose the respective solutions. We also analyze the impact of SecML on other qualities, including fairness, explainability, reliability, safety, and sustainability. This research work can be used as a research map for machine learning or software engineering researchers and practitioners towards more secure, reliable, and trustworthy MLOps. Future work are required to fully realize our vision and validate the SecMLOps. So here are some references, and thanks all for listening.
Thank you very much, Xinrui, for your wonderful presentation. So far we've heard a little bit about the security challenges for machine learning and AI-based systems at the architectural level. We've heard a little bit about security challenges when we have the overall deployment and operation of these types of systems, when we look at it from this kind of DevOps perspective. The notion of SecMLOps is very interesting in terms of providing an overview of the different kinds of security considerations that we need throughout the entire life cycle of an AI-based system, for example. So in my presentation that will be happening right now, I'm going to focus now on the assurance aspects of some parts of different kinds of AI-based systems. And in particular, we're going to focus in on deep neural networks. And the idea with this presentation is that we are going to look at how do we ensure, or assure that is, that the systems that we build that contain these AI or machine learning based components are in fact behaving as we expect them to, and are addressing those various security challenges throughout their different parts of their life cycles. So again, we're going to talk a little bit about security assurance for deep neural networks. So to start us off, a deep neural network simply is any type of artificial neural network that's made up of multiple layers of interconnected nodes that we call neurons. Typically, a DNN will comprise of one input layer, one output layer, and one or more hidden layers. The structure of a DNN is shown on the slide here. So we have the input layer, the output layer, and some number of hidden layers. And an activation function is used to transform the neuron's outputs before passing it along to the next layer. So this is the way that a DNN will work. DNNs are typically designed to recognize patterns and to help make decisions by learning from large amounts of data. Now, in our society, DNNs have found a widespread adoption. They've been introduced in a number of different industries, thanks to the different kinds of results that they can achieve. And in fact, these DNNs are finding their way into a number of safety and security critical domains. So for example, we find DNNs in automotive systems, such as those within an autonomous vehicle, for example. We find it in air traffic control systems. We find it in healthcare and medical diagnosis type systems, in energy management systems, in financial systems, as well as in emergency response for, say, fires, for instance. So with the introduction of these deep neural networks within these safety and security critical domains, this, of course, introduces a number of potential new risks that we therefore have to deal with. And many of these risks are the kinds of things that we have heard about already in our session today. So when we're developing these kinds of systems, like an autonomous vehicle, for example, or like a medical diagnosis system, when you use these deep neural networks, you want to have some assurance that they are in fact working as expected. For instance, if you have a pedestrian detection system within your autonomous vehicle, you want to ensure that you actually are detecting pedestrians that are in fact there. You don't want to detect pedestrians that are not there, and you don't want to miss detecting pedestrians that are there. As you can imagine, that can result in a number of very serious consequences. The same goes with something like a medical diagnosis system. You want to ensure that the system is going to behave as expected. So if you're identifying within a medical image some sort of disease, such as cancer, it's critical that you do, in fact, identify the actual disease. The introduction of false positives and false negatives can have severe consequences. And this goes for any of these type of systems that are operating under normal circumstances. But when you introduce attackers into this picture, well, that's when things get a little bit more tricky, because all of a sudden you can fool a system into thinking that there's a pedestrian when there isn't, or thinking that there's a tumor when there isn't, or thinking that there isn't a tumor when there in fact is, for example. And again, this causes a lot of trouble when we are thinking about how do we design these kinds of systems and engineer these types of systems to be able to operate in our society, where the people or the users of such systems are going to have a certain level of trust in them. And to introduce an example of the need for this greater level of assurance, this is in fact a real world example of an Uber autonomous vehicle that was being used in Tempe, Arizona. So in this specific system, DNNs were used to build a pedestrian detector for the self-driving car. It's ADS, automated driving system within this Uber vehicle. And it turns out that what happened was this vehicle was driving and it failed to detect a pedestrian that was crossing the street in front of it. And basically, after an extensive evaluation of what actually happened, the National Transportation Safety Board within the United States determined that the vehicle was having difficulty in determining or deciding whether or not it was in fact a pedestrian that was crossing in front of it. So it kept alternating between thinking that this was a pedestrian or not, and then a pedestrian again, and then not. And it never actually was able to come to a conclusion within the time that it needed to. And it resulted in striking this pedestrian. And unfortunately, the pedestrian passed away as a result of this collision. And this just goes to show some of the criticality that these systems have, is that not only are they performing these very critical tasks, but they're often very strict or complex requirements in terms of the real-time decision-making that these systems need to have. So this is an example of just some of the terrible consequences that can happen if these systems aren't built in such a way to ensure that they behave as expected. Now, what I want to be clear about is that this example is not a case that was caused by a security incident specifically, but instead, this case exemplifies the different concerns that can arise if we have a malicious attacker added into this mix. So again, all of a sudden, if a pedestrian is passing in front of the vehicle and an attacker can cause the vehicle to enter into this position of indecision, well, we can result in the same kinds of outcomes. So again, this attacker might exploit the lack of a learning phase or tamper with the different entries for the data to the DNN to force a self-driving car, for example, to behave in many different dangerous ways and possibly cause these kinds of accidents. So what this example shows us is that for these kinds of safety and security critical domains, we need to question the trustworthiness of these systems that are all of a sudden using these emerging technologies that perhaps the engineers using these technologies don't have a deep understanding of. And we need to establish the justified confidence that the system that incorporates these kind of components that are based on deep neural networks, for example, are designed and behave in a safe and secure manner. So when we consider this issue of assurance for deep neural networks, we arrive at a number of key challenges. The first is that DNNs are known to be vulnerable to a wide range of security threats. And we saw this in the earlier presentations that we had in our session today. There's the issue of adversarial examples. There's the issue of model extraction or model inversion type attacks. These data poisoning attacks, overfitting type attacks, as well as Trojan attacks. These DNNs are vulnerable to these wide range of threats, not to mention that the systems in which these DNN-based components are being used in are also subject to all of the different threats and challenges that a classical software-dependent system would be facing as well. So the assurance of the DNN has to consider those traditional issues, but it also has these unique challenges. So it differs from the classical systems because a DNN is also data-driven, and it has some characteristics that are quite different from those classical systems. So generally, when we're using DNNs in a security critical system, it requires that we provide assurance that shows with some sufficient level of confidence that the system's going to perform its tasks safely and securely. But security in this context is quite an open problem because it combines all of the human, the technical, and the organizational problems that come with this system and its domain of operation. And the evolving nature of all the different threats indicates that there isn't going to be a one-time solution for this. There's a new environment where information may arise over time. So the need for security assurance within DNNs is for these kinds of data-driven applications and for the development of the algorithms that these DNNs are using, and such that they provide some provable security guarantees. Now, in order to provide this kind of assurance and to address this key challenge, we have to be quite careful about what we're really focusing on. Now, in today's talk, there's not going to be enough time to talk about every single aspect of this issue of security assurance for DNN development. Instead, we're going to focus on providing at least some security assurance for DNN development. So on the slide, what we have is a traditional DNN development lifecycle where we have a requirement stage that's going to feature some requirements analysis. And this is going to fit into a data-oriented stage of development where we have tasks related to data collection, related to data preparation, related to feature engineering, and data allocation, which is then going to be used in the model-oriented stages of development where we actually design the DNN, we perform some training of that DNN, and then we evaluate and iterate throughout these stages before ultimately going into our operational stage where we deploy the DNN and monitor its performance over time. So when we consider this, deep learning is really just a subfield of machine learning, and it's data-driven. And what that means is that the behavior of a DNN-based system is really learned from the data that it has. So concerning a classical system, DNNs require these new development activities, as we can see in this illustration on the slide, with these different data-oriented stages, for example. So therefore, we can conclude that assuring the use of a DNN in a critical system is going to require a deep understanding of this DNN lifecycle to ensure that all of the different artifacts that we generate during this DNN lifecycle are going to be sufficient. So to further understand this, we can basically study these different lifecycle stages and determine where these high levels of assurance are going to be required. So in what we are going to talk about today, we're going to want to provide some security assurance cases that consider these different DNN development activities. And in order to do this, we're going to focus on two main aspects. First, we're going to focus on demonstrating that the DNN has been developed adequately with consideration to the various security concerns at all stages of the development lifecycle that you see. And the goal here is to argue that the DNN complies with the necessary processes and procedures and activities to support claims that we've developed the DNN to have what we call adequate security. You can think of this as just being secure enough for the specific operational environment that we expect the system to operate in. So we refer to this really as the secure development, right? So the basic idea is that we need to decompose the processes that are involved in the development of a DNN to ensure that each one's been adequately performed to support the claim that the DNN has been developed in such a way that security has been adequately considered. And the idea is that if we have a poor decomposition of these processes, then that can lead to missed processes or procedures that can leave the development of the DNN as being inadequate in terms of the different security considerations and compliance requirements we may have for the system in which it's being used. The second task we're going to perform is really focused on demonstrating that the DNN is satisfying all of its security requirements. So the goal here is that when the DNN completes its training with its specific decision logic, we want to understand how it systematically evaluates its generality and quality through some sort of verification or testing. So we want to argue that the tests and or formal verifications that we perform on the DNN support the claims that we've actually satisfied all of the specific security requirements that this DNN will have. So really, the assurance argument we want to provide should demonstrate the relationship between the verification or testing evidence that we have and the security requirements that we have. And again, the basic idea of these two aspects isn't that much different from what we would do when we're providing security assurance for a traditional software-dependent system. But the fact that we are dealing with these DNN components within these systems requires us a little bit more attention to the way in which we consider the DNN development according to the stages of development for these deep neural networks. Now, in order to provide some of this security assurance, we can look at developing security assurance cases using this notion of argument patterns. So what an assurance case is it's simply a structured argument that's supported by some evidence, providing clear and compelling justification for the safety, security, or reliability of a system. And when assurance cases claim system security properties, we simply call them security cases. And security cases are important because they record our reasoning so that others can learn from the way in which we reason about the security of a system and ultimately buy in to have some confidence about the claims we have that our system is in fact secure or adequately secure. That is, again, secure enough. Now, in order to develop assurance cases, we also have this notion of argument patterns. And argument patterns are simply reusable templates of the different types of claims and evidence and justification and all of the contextual information that we can use that must be covered in a compelling argument to support those specific claims that we have. So security argument patterns really just help to construct a security assurance argument by maintaining the structure of the argument and generalizing specific details so they can be instantiated in different situations. This notion of an argument pattern is not all that much different from the idea of a design pattern, for example, in traditional software development. It provides a general reusable solution to a recurring problem. You need to argue about the assurance of a specific aspect of your system. So there's a typical pattern of argumentation that you can follow to provide that convincing argument that is needed. And ultimately, the use of argument patterns helps to facilitate the reuse and incremental refinement of these assurance arguments that we're trying to provide, especially considering that different systems that we have may be subject to different standards and requirements in different application contexts. So in order to provide this kind of assurance case and to propose these different kinds of argument patterns, we use a language for representing assurance cases called the goal structuring notation, or GSN. The notation is shown here on the slide. So the blue rectangle shows a goal or a claim that forms part of our argument. The green parallelogram here represents a strategy which describes the nature of the different kinds of inference that's existing between a goal and any of its supporting goals. The reddish colored circles or ovals represent solutions. They provide a reference to a specific piece of evidence that allows us to support a specific claim. We have a number of these yellow nodes. This sort of rounded rectangle represents a context, which allows us to describe a contextual artifact that is important for understanding the argument that we have. We have assumptions, which are intentionally unsubstantiated statements that we include in our argumentation. And we also have justifications, which provide this explicit rationale for a particular inference or strategy that we might use in order to argue about a specific claim. Now, in an assurance argument, we have a number of other decorations and relationships that we can use in relating all of these different elements. So we may choose to have specifically undeveloped entities where we simply require more development of the argumentation that we have. The uninstantiated entity is usually applied to an element type, denoting that we need to instantiate it with a more concrete instance at some later stage of our argumentation. These are usually defined with some sort of token or parameter that's instantiated at a later time. And this is particularly used when we have these argument patterns so that we can instantiate them in the particular context in which they're being used. And then the relationships basically give us the options of describing whether we have a claim within a specific context, whether we have a relationship of support, whether we have optional supports or alternative relationships between different elements, or whether we have alternative choices in the way in which we can satisfy a particular relationship. So again, this gives us a nice graphical notation for representing these assurance cases and argument patterns. So why would we talk about assurance cases and argument patterns? What's really the point about this? As I mentioned earlier, security combines the human, the technical, and the organizational problems that we have. This evolution of threats means that we don't have this one-time solution. We have to be able to account for this new information that arises from this different operational environment. And what is beneficial from developing these security assurance cases is that, again, they enable us to record our reasoning so that we can basically have it explicitly documented and open to review and criticism by other stakeholders of our systems. And why argument patterns is, again, argument patterns give us that reuse and incremental refinement of our arguments. As I mentioned, the different standards and requirements in the different contexts may require different refinements of these arguments to be tailored specifically to those particular application domains. So the way in which we're going to talk about security assurance for DNNs is by proposing a couple of these different assurance argument patterns that can be used for deep neural networks. So the first pattern that we describe is the DNN secure development pattern. And the goal of this pattern is to provide a convincing argument that the DNN under development complies with the necessary processes and activities to support claims that the DNN is adequately secure. So the basic idea here is that the DNN development pattern is going to show that the earlier activities of the DNN development, where the security requirements must be satisfied, is in fact done in an appropriate way. So this pattern is typically for a single DNN component, and the requirements of that DNN component have been identified by considering a broader system context, including defined security requirements derived from the overall system security process. And the basic idea here is that we would apply this pattern whenever we need to demonstrate compliance in the secure development processes for the given DNN. So the pattern assumes that the relevant development methodology provides sufficient context for its instantiation. So you can see this DNN secure development pattern on the slide here. And again, we're using the goal structuring notation that I described just a little bit earlier in order to capture this pattern. So at the top level, you can see a goal here. And this goal is focused on demonstrating that the DNN development satisfies its particular security requirements. And this is within a specific context. And that context is within the description of the specific DNN under consideration, as well as the description of the specific system under development. And here we're going to assume that all of the security requirements are in fact elicited by some process that we would have. Now, in order to demonstrate that this goal is satisfied, i.e. that the DNN satisfies its security requirements, we're going to argue through all of the different DNN development stages. So first, we can look at the data-oriented stages satisfying the DNN security requirements. And again, we have a little decorator on the goal G1 here that shows that this is an undeveloped goal. It means that we need to further develop this in an instantiation of this pattern to clearly demonstrate that this claim is in fact supported by some sort of evidence. Here we're going to focus more on the model-oriented stages of the DNN security requirements. And really we want to focus on arguing through each of the model-oriented DNN activities that they satisfy the list of security requirements that we've elicited. So when we have a description of each of those model-oriented DNN activities, we really are just going back to our DNN development lifecycle, and we're arguing that the DNN architecture through the design activity is appropriate to satisfy the requirements, and that the DNN training is appropriate to satisfy the requirements, and that the trained DNN that results from the training is satisfying the security requirements that we've identified. And the way in which we're going to do that is we're going to argue through the satisfaction of each and every one of the requirements that we have. So for each requirement, we're going to show that the trained DNN satisfies that specific requirement. So it's really this decomposition of the process within our DNN lifecycle that we're going to make this argumentation to support the overall claim that we've developed the DNN in such a way that we satisfy the different security requirements that we have. So this is the first pattern that we have, and it corresponds to really that first part of providing the security assurance for the DNN that I talked about a few slides earlier. The second pattern that we have is really going to be related to the bottom here, where we're arguing about the trained DNN satisfying each of its security requirements. We can see that this is, again, an undeveloped goal and that it requires further development and support in order to demonstrate that it is, in fact, satisfied. So to do this, we have another argument pattern, which we call the DNN security requirement satisfaction pattern. And this is really focused on providing a convincing argument that the trained DNN satisfies its security requirements. And this pattern can be applied whenever a compliance is required to verify the fulfillment of the security requirements of your DNN. And again, the pattern is going to assume that the relevant standard or development methodology provides some sufficient context for its instantiation. So in providing this argumentation that the requirements have been satisfied, we really can focus on two kinds of evaluation. The first is test-based evaluation, where we're going to utilize test data to demonstrate that the model for the DNN generalizes to cases that aren't present in the model learning stages. The alternative is to have a formal verification that use, for example, deductive methods or abstract interpretation or model checking aimed at verifying that the model of a system satisfies some properties on some mathematical basis. So what I want you to pay attention to is that the top level goal of this pattern is the same as the bottom goal that we saw in the DNN secure development pattern. This idea that the trained DNN satisfies its particular security requirements. And this is applied to each and every one of the security requirements we have. So it's done within the context of that specific security requirement. And we're going to argue through the specific evaluation method that we use. So as mentioned, we could either do this, and that's what this black diamond here denotes, is a choice between using the test-based evaluation or a formal verification-based evaluation. So should we choose tests, we can say that the security requirement is satisfied using the test data that we have. We would have the test data provided, and we would show all of the results of our testing in support of that claim. And of course, if we have sufficient test results, then we can argue that we have satisfied the particular requirement. The alternative is to provide a higher level of assurance using formal verification or some sort of formal methods. So in this case, we can describe that formal method and argue that the formal specification and verification of the security requirement is in fact appropriate for the given requirement that we have. So this breaks down into showing that the specification for the property that represents that requirement is appropriate, and that can be done and supported by evidence showing that there's agreement by inspection of domain and formalization experts. And in addition to that, we also need to show that the formal model that we have satisfies the formal specified property. And this will typically be supported by our formal verification results. So if we have, for example, model checking, we will have the results of our model checker telling us whether the property is satisfied or not satisfied, for example. So again, this is not terribly different from what you would do in providing assurance that a security requirement is satisfied for any traditional software-based system. But instead, the way in which we have to consider the challenges associated with the DNN development is where this becomes interesting. Now, in order to best understand how all of these different assurance arguments and cases are developed, we can look at an illustrative example. So here's an example of a system that is an airborne collision avoidance system for unmanned aircraft. The ACAS system is what we call it. Okay? So the basic idea here is that this system uses a DNN for decision-making in the presence of what we call an adversarial intruder. So the basic setup is that we have a number of unmanned aircraft. In our example, we're going to consider just 2 aircraft. One we're going to call our own ship. That's the ship that we are interested in controlling. And we're going to have other ships. In this case, we're going to call them the intruder, that enters into the airspace of the own ship, and we want to avoid collisions with our own ship. Okay. So in this context, the DNNs that are used are really trying to decide how the own ship should behave in order to avoid collisions with other aircraft. Okay. So again, we're going to just consider encounters between these 2 unmanned aircraft, and we're going to take the perspective of the own ship. Okay. Now, in this system, we have a DNN that is consisting of an input layer with 5 inputs that include the distance between the own ship and the intruder, the velocity of the own ship and the velocity of the intruder, and the angles of approach of each of the 2 ships as well. And then there are 6 hidden layers. Each of them contain 50 neurons each, and they result in an output layer that will give us a number of different possible outputs. The first being COC, which means clean of conflict. This is the basic idea that we're not in conflict or in a situation where we might collide with the intruder. Therefore, the system can do nothing and continue on its course. Otherwise, we're going to find that we are in a situation where we have a potential collision, and we can result in a number of adjustments to the heading of our ship, either a weak or strong adjustment to the right or to the left, depending on the specific situation. Now, what's interesting about this particular system is that you can right away see that there are 6 hidden layers with 50 neurons each. And the basic inspection of a DNN of this size is simply not possible by a human. So therefore, we have to take into consideration these additional ways of verifying the behavior of this kind of a system. And it's important to note as well that in this system, we use an activation function, which is known as the rectified linear unit, or ReLU activation. This is one of the most popular activation functions used in practical hardware and software implementations of DNNs. So this gives us the basic setup we have for this system, right? But what happens when we need to provide some assurance that this system is performing in such a way that we're going to avoid these collisions? Now, one of the things we have to consider is that in this system, this ACAS system, there's a threat of adversarial examples. And we've seen quite extensively throughout the day, I believe, a number of different definitions of adversarial examples, these well-crafted inputs that are obtained by slightly modifying our sane or initially well-classified inputs that are used to deceive a DNN or a machine learning model by forcing an assignment of a given input to a class to which it doesn't belong. So formally, what this means is that given a DNN that assures some function f, the attackers are going to find some minimal perturbation to add to a sane input x to obtain some new input x prime, such that f of x is not the same as f of x prime. So this is best understood by a very simple example where we have our own ship and our intruder. And the idea is that in this situation, we can see that just visually, these two aircraft are on a course to collide with one another. So in the operation of the ACAS system, the own ship should predict a left turn, as we can see in the top part of this figure, to ensure that we don't collide with the intruder. And the problem is that with adversarial inputs, it's possible that even in this scenario, the DNN can be fooled into believing that instead of a left turn, we need to take a right turn instead, as shown in the bottom part here. That would directly result in a collision between the two ships. So in this case, if the DNN isn't verified, there may be these specific situations where this collision avoidance system, for certain approaching angles of the different ships, advise the ship or the aircraft to incorrectly take the wrong turn, leading to collisions instead of avoiding them. So basically doing the exact opposite behavior of what we would expect. So the problem is that if an attacker knows about the presence of these adversarial cases, they can specifically approach intruder ships at adversarial angles that will cause these collisions to happen, despite the DNN doing its best to avoid such collisions. So in order to assure the behavior of the ACAS system using our argument patterns, we can go ahead and we can instantiate them. So in the specific context of the ACAS system, we can instantiate our DNN secure development pattern. So the primary requirement of the DNNs within the ACAS system, of course, is to avoid collisions for any malicious input that's provided by an attacker within a specific input range. And we have a number of different security requirements that are associated with this high-level requirement. The first is that if the intruder is distant and significantly slower than the own ship, the score of a clean of conflict advisory will always be below a certain fixed threshold. And security requirements 2, 3, and 4 are along the same lines, describing specific situations that describe when we're in a clean of conflict situation, for example. And we want to ensure that this is always going to be the case, right? So to apply our DNN secure development pattern, we need to instantiate all of the parameters in the uninstantiated elements of the pattern itself. So for example, the name of the target DNN is instantiated to be the DNN from the ACAS system, for example. And the pattern application basically focuses on providing those different context elements. And that's what you can see on the slide here, is that we've now taken all of those contextual elements that had a number of parameters, and we're instantiating those parameters with the concrete elements from our system. So in this case, context node C0 describes the DNN, its functionality, its inputs and its outputs, as well as its activation function. Node C1 describes the system in which the DNN will be deployed. In this case, it's the ACAS system, which is a collision avoidance system in an unmanned aircraft. C2 includes all of the security requirements we have, and C3 describes all of the DNN design activities. So the basic idea here is that for each of the security requirements we have, and again, R1 through SR4 is just a small subset of the different security requirements we would have for such a system, we would have a specific goal that is used for describing the trained DNN satisfying each and every one of those requirements. So although this isn't really an exhaustive list of the requirements, it represents some of the most important requirements for a component like this in a similar type of system. So in our case, we're simply going to assume that all of the security requirements are elicited, and this provides us with the basic argumentation that at least from the training and eventual operation of the system, that the trained DNN is going to satisfy its requirements. Now, of course, when applying this pattern, we have still a number of undeveloped goals, which means that this isn't a complete assurance case. We would need to provide all of that information. We simply don't have the time to go through all of those details during our talk today, but hopefully this gives you the basic idea. Now, as we saw earlier, when we need to go through each of these requirements now to support all of the goals, G 6.1 through 6.4 at the bottom of the slide here, we want to ensure that the trained DNN satisfies those requirements. Now, the way in which we do that is for each of those requirements, we can go ahead and we can apply our DNN security requirement satisfaction pattern that we described a little bit earlier. But again, if you recall that pattern, what we need to do is decide, are we going to use a test-based evaluation or are we going to use a formal verification-based evaluation? Well, it turns out for a system like ACAS, there is a formal verification method that we can use that's called interval analysis. Now, interval analysis is not something we invented, but it's something that exists that can be used for DNNs of this type. And what interval analysis is simply a method that studies the different arithmetic operations on intervals of inputs rather than on concrete values. So the goal here is to follow the exact arithmetic that's performed within the DNN to compute all of the different output intervals that will basically give us the ranges of outputs that would lead to specific classifications. So based on those output intervals, we can then verify the different kinds of input perturbations that would lead to violations of the specified security properties over those specific intervals. Now, fortunately for us, we have a tool that's called ReluVal. That's basically a system designed to formally check security properties of ReLU-based DNNs. So remember, for the ACAS system, the activation function used in the DNN is the ReLU function. So what ReluVal does is it uses these symbolic intervals whenever it's possible to track the lower and upper bounds of each neuron within the DNN. So the basic idea is shown on the slide here, is that we have a target DNN and a specific security property we want to check. And basically the tool itself is going to perform that check using these intervals. And it's ultimately going to decide whether the system is safe, i.e. the property is satisfied, or it's going to find that there was an adversarial example found and provide that counterexample which describes that scenario, or we will have a timeout from the tool, which more often than not means that there is some issue either with the model or with the verification that usually indicates that there's a situation where it can't decide whether it's safe or not, which means we have to do something to determine, because a timeout doesn't imply safe, for example. So what we're going to do is we're going to use this notion of interval analysis to help us instantiate our DNN security requirement satisfaction pattern. So we're going to focus just on SR1. So just one of the security requirements we would have to do something like this for each and every requirement. So as you can imagine, this becomes quite a significant amount of work, but it's required to provide that confidence and overall assurance that the system we're building is in fact achieving the behavior that we expect. So the basic idea here is SR1 requires bounding the confidence score of the clean of conflict output for our DNN and never trusting the situation quite too much, okay? So what this means is that we have to, if we choose to use formal methods, which is what we're doing in this scenario, we have to specify that requirement as a property. Now, the property specification is shown in red on the slide here. There appears to be a number of magic numbers in this property specification. When we look into the ACAS system, there are works that describe the specific intervals and tolerances for the distance and the velocities of the various aircraft, as well as the thresholds for the specific scores that are generated by the DNNs. So these are not numbers that are just miraculously made up. There is, in fact, analysis that goes with them. I'm not going to go into all the details of all of that here, because that's not really the important point to take away. The important point is that we have a specification of this property. And once we have the specification of that property, we can use an appropriate tool like ReluEval to formally check whether that property is satisfied for the given DNN that we have. So when we look at instantiating our security requirement satisfaction pattern, we have chosen in this particular instance to use formal methods as the evaluation method. So already you can see in the instantiation of the pattern that we no longer have the branch that shows all of the testing based evaluation, because we've elected to argue through the formal verification instead. And one of the rationales that we would provide for using an appropriate evaluation method like formal verification in this case is that, for example, this security requirement SR1 requires protecting against an adversarial example. And test-based methods are really useful for finding adversarial examples, but they don't provide any formal proof or guarantee about their absence. And because of that, we may choose to use formal verification because we'd rather demonstrate that there are no adversarial examples rather than showing that there are. So what we do is we then say that SR1 is satisfied using formal methods, and we're going to specify the formal method that we use as interval analysis, which will be helpful for verifying that security property of the DNN. So we argue over the formal specification and verification of the security requirement. So the goal here is to demonstrate that property 1, as shown on the slide in red, is the appropriate formalization of SR1. And the evidence to support this is that there's agreement over inspection conducted by domain and formalization experts about the choice of the different threshold values. So I mentioned that the specific numbers that appear in that specification are actually chosen through an analysis. So that would be enough evidence to support that the values that we're using are in fact sufficient for formalizing this requirement. And the second part of this is to actually show that the formal model of the DNN satisfies that specific property. And in this case, we can use ReluEval to check this property, and we can provide those results in order to demonstrate that the property is in fact satisfied by our DNN. So now suppose that we do something similar like this for each and every one of our security requirements. And that way, we show that all of our security requirements are satisfied by our trained DNN. And if we assume that we develop all of the nodes within the secure development pattern, then we argue that throughout the development of our entire DNN, we have done all of the activities with supporting evidence showing how those activities were done to support the claim that the DNN has been developed in such a way that all of its critical security requirements are in fact satisfied. And that then provides a convincing argument that the DNN is expected to behave appropriately, even in the presence of these threats, such as adversarial examples, for example. Now, again, I've mentioned this before, and I'll mention it again here, is that this is a large undertaking. It takes a lot of effort to provide all of these assurance arguments. But one would argue that when considering engineering a secure system, all of this testing and verification, as well as the design evidence that you would have from your security requirements elicitation to the architecture design to the overall and eventual operation of your system, is all part of your system development lifecycle anyhow. So typically you're performing many of these tasks. What this assurance activity is doing is really coalescing all of the artifacts that you're generating throughout that development lifecycle in order to provide a convincing argument that the system that you've developed is secure enough for its particular operating environment. So just to bring some concluding remarks to the presentation here is we can see from just this talk alone that security assurance of DNNs is rather complex and challenging. It requires a specific understanding of the DNN development lifecycle. Argument patterns and assurance cases can enable security engineers to determine those DNN-specific security considerations that we might need in order to evaluate the security of an AI-based system. So these argument patterns really help to support evaluating the security of the system that incorporates those DNN components. And again, all of the argumentation that we've talked about in this specific talk is focused just on those DNN components and not necessarily all of the other components that comprise the system as well. Now, we've talked today about DNNs, but of course, other types of machine learning may also benefit from this kind of guidance, particularly regarding the security requirements and the data management that we describe in the different argument patterns. Underpinning all of these argument patterns is simple argumentation that's rather domain independent. Instead of instantiating this in the context of a DNN, it could be any other type of machine learning model, like a convolutional neural network or whatever. The considerations may be slightly different in terms of the way in which you provide the evidence and the supporting tools and technologies that may be able to help in that context, as well as the specific challenges that may come with these different types of machine learning. But generally speaking, the basic ideas will remain. Now, of course, this is just scratching the surface of this issue of security assurance for DNNs and AI-based systems at large. So there are several areas for further work that exist. I'm just going to name a couple of them here. So one is we can look to try to develop an assurance process that ensures the security requirements should be generated from some rigorous threat analysis. In the patterns we described in this talk, we basically just assume that the security requirements exist without really giving any details of how they would be developed or understood in the first place. So a threat analysis could help to dictate not only the classical threats that would need to be guarded against by these types of systems, but also the deep learning specific threats that would be unique to this system. And again, if we consider this beyond the scope of DNNs alone, the other specific threats related to the specific learning technologies that may underpin the AI-based components that we have. Another thing that we need to do is also give attention to the data-oriented stages of DNN development. We focused very much in this talk on the model-oriented stages in terms of the trained DNN satisfying all of the requirements. But DNNs are data-driven and many security threats can appear in the data-oriented stages. So in order to provide full assurance of the DNN, we can't ignore those data-oriented stages as well. And lastly, we can also look to provide domain-oriented argument templates by choosing specific argumentation strategies that are sound within specific domains. So I mentioned off the top of this presentation that there's a widespread use of DNNs in a variety of critical domains, everything from autonomous driving to air traffic control to emergency response to finance to healthcare, for example. The current patterns are domain independent and require some specific domain knowledge for their application. But we could imagine providing some specific argumentation and justification along the way that would be most relevant in a healthcare context, for example, or in an energy management context, or in an autonomous driving context, for instance. So it's important that we can also explore those specific characteristics of the operational domain that may, in in fact, provide extra guidance when trying to provide assurance for these complex systems within not only these critical domains, but these domains that have large and significant complex systems as well. So that will basically summarize what I have for today's talk. There are a number of related publications and references. Specifically, I want to acknowledge the fact that much of the work that I presented here was done in collaboration with Marwa, who presented earlier in our session. So special thanks to her for the awesome work that she's been doing in this space. It really just helps to have these larger, broader collaborations worldwide for advancing this research in these very critical topic areas. So with that, I thank you all very, very much for your attention. And if you care to learn more about the Cybersecurity Research Lab, you can certainly find us on the web. On LinkedIn, we have a page there that we provide a number of updates and posts about what we're up to. And I'm happy to answer any questions that we might have in the remaining time for our session. And as we wait, if there are a couple of questions coming in, I will simply just stop the screen share, and I will look into trying to provide some summary of what we talked about here. So, of course, securing AI-based systems is not a simple task. I've mentioned it in my talk. We've seen it in all of the talks throughout our session this afternoon, that these systems are large, they're complex, they have many, many intricacies and unique challenges that make engineering them in a secure manner very, very difficult. We are only providing just a scratch on the surface of trying to develop these systems in a manner where they can be considered secure and trustworthy. And we focus on the idea that this has to happen at all stages of development, starting from really understanding the threats and the requirements for protecting these systems against the various threats that they have, to designing these systems in such a way that they're resilient and robust with respect to these threats, to then implementing these systems and testing, verifying, validating these systems, and continuously monitoring their performance in terms of security as they move into deployment and operation. And without performing all of these activities and considering all of these unique challenges, it's very unlikely that we're going to result in systems that we feel safe and secure in using for the long run. AI-based systems have great promise. We can see that. We see their use in so many different types of systems, different kinds of domains. And they have this promise of great benefit, but with that great benefit comes this great risk that we need to manage. And our hope is that the work that we're performing and the research that we're doing within the Cybersecurity Research Lab at Carleton University is at least helping in some small manner to solve this colossal challenge that we have. So with that, I think we'll wrap up our session. I want to thank everybody who presented today. Marwa, Xinrui, thank you very much for your presentations and participation in today's session. I'd like to thank the SECREV organizers for having us. It's always a pleasure to be able to contribute to this wonderful event. And I'd like to thank all of the attendees watching on whatever streaming service you're watching on for hanging out with us this afternoon. And we hope that this provided some insight and some food for thought for how we can move forward in the future with these really exciting, but also terrifying technologies. So thank you very much, everyone. Have a great rest of your day.